All right, so we're back to System on a Chip. We're going to be talking a little bit about some kind of features inside of System Verilog, and in particular some ones that may or may not be comfortable with people on how we can build some things. We will be actually talking, we were just in pre-class talking a little bit about multipliers and that. I plan on using an example using an adder, which you're probably familiar with, but to get you used to another construct that you may or may not have seen called the generate. So we're going to talk about some things, but before we get to it, I do want to talk about something that the book doesn't talk about, but that kind of, it's under the hood in both Verilog versus System Verilog, which has to do with timing and how things happen on the simulate. We talked a little bit about some of this, a little bit deeper than the book goes, where we talked about why, for instance, we do, a non-blocking versus a blocking at times, and sometimes we do blocking versus non. So it's helpful to know some of those simulation sequences that's going in. So let me talk for a sec here about, actually even before I do that, maybe I should step back 1 second, talk about what our rules were. Does anybody remember what our rules for blocking versus non-blocking assignments?
Combinational use blocking, flip-flops use non-blocking.
Right. So if I'm doing combinational logic, I want blocking, and for my sequential, I want non-block. Right? And remember, we showed like a simple example where you could get very goofy behavior if you did not do this. Right? And we just did that one from kind of a practical area. And remember, the key was blocking updates happen before non-blocking do. Right? Blocking ones we can sometimes think of as instantaneous assignments. The second it sees it, it just assigns it. Whatever the current value is, just go. Right? Whereas non-blocking, I take what was the previous state, I wait to the very end till everything settles, and then I do my assignments. Right? So different types, you don't want to mix those on them. So that's another kind of one of those basic rules. Inside any block, don't mix. But let me talk about the sequence that goes on inside System Verilog, and then I'll tell you a little bit how that's different than regular Verilog. So whenever I do any timing step, okay, and technically the word step is a bad choice now, it's the old word. Now they talk about these time stops that are in there. But the idea of this is that I've got a smallest time unit that's on. And when I go to do a simulation, I've got some initial instant and the next instant. Now the smallest instant that I can do is actually recorded for me. But if you remember, we have these little timescale commands that are out there, and there's two numbers to them. The first number is what's the actual, when I'm going to do my simulation, what is that smallest unit of time. But there's actually a smaller one, which is that second number. They can be equal, or that second number can be smaller. That's the resolution. So that's what it's calculating at. Now globally, right, I have, of all these, I could have different time scales that are set out. What does this mean? Right? Is it always a nanosecond?
It's the first one.
Yeah, it takes a look at whatever that scale is inside there. Now, what's the smallest that I can do? Right? I could technically define them even smaller than that. So how do I know what's the smallest one across all my units? Okay? This one looks globally and takes the smallest one. So between any two time simulation steps, this one is defined as that smallest. You cannot synthesize this. It is not a good synthesis. Well, it's really more meant for simulation, and it's really meant for verification. So when we're going to talk about verification in a bit, this becomes kind of an important concept that goes in. And so I at least want to talk timing-wise how these are going to go. This becomes kind of an important step that's in here. Now, this one can change its meaning based on I load a new module, away we go. If all of them are using the exact same timings everywhere, these two are identical. But if you add a new module and it's got a smaller time unit, this one actually will still give you the smallest step you can make. And this becomes really important for when I'm building things. Now there's one other weird construct that's out there. It's this. Right? What does that technically mean?
No time.
Wait no time. Right? So therefore it shouldn't matter, should it?
Different phase.
Yeah, this is where we get into the phases. So never ever do this, but you might see this in a design. I'm going to explain where it comes from a design. I'm going to explain why I don't want this to happen. Right? This is dangerous, but I have seen it done quite a bit. When you look at system Verilog and its timing areas, there's really four major phases that go on. Right? So we've kind of got this a pre-step that goes on, and then we've got the active set. And then I've got a reactive step that I got a post. And sometimes people put in between kind of a monitoring step. So we break them in. Now, the active step and the reactive step are broken into 3 units, right? That are an active and inactive, and then this kind of final cleanup one. And that final cleanup, this is where non-blocking assignments are done in the last. This middle one is where the wait no time ones happen. So it actually happens at a different stage inside that simulation. And the very first one, this is where blocking happens and a whole ton of other stuff, right? This is also where $ display happens. This is where if you have a continuous assignment, it happens. So this is like almost everything. This one is kind of this weird time unit that happens only for these, but it's after everything else. And then there's the non-blocking assignments. So some people do it to kind of force a time sequence into their design where otherwise they wouldn't know it. So it makes their time sequences deterministic, and that makes it easier for them to predict what it's going to do. The problem is you can't synthesize that. So now you have guaranteed that your simulation is going to have a particular behavior you believe in. It will never give you a non-random behavior, but your actual system is guaranteed not to have that performance. So you have essentially forced your system in its simulation to behave differently than it will when you synthesize it. So by forcing it not to behave in the same way, that's why I call that innately dangerous. If you need to force that type of sequencing, you should force it in a way that's actually synthesizable, not in a way that's non-synthesizable. So this is why I say, no, no, no. And every major person I know says, no, 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 never ever do this. That being said, a lot of people go, ooh, a quick, easy way to fudge things. And so you'll get a lot of people who do it. If you see it, just consider the whole code dangerous, right? That's kind of my innate reaction. I might not say it to their face, but I'm certainly, if I'm having to deal with that code, I'm going to assume they've done other wacky things, because this will guarantee that your synthesis and your simulation are different. No good. Right? That's these 3. It'll do the same thing here in the reactive set. Anything changes in each one of these, and it will rerun. And they kind of flow down. So this is why if you change something that's possible, one of the variables you change might be an input on the other side. So it'll keep doing this until nobody changes inside, and then it'll move to the next one. This reactive one, so this was the basic setup of how you had it inside of Verilog. System Verilog added these down here. Because this allows me, we ideally want this reactive one to be where all of your control for a test bench is going to go. Now, the reason why we want this is I don't want there to be a race between my test bench monitoring functioning that's reacting to the system and my system itself, which is actually doing it. Because now I've made a weird coupling between my test bench and my synthesized logic. So System Verilog said, I'm going to separate these two things so that I'm in a stable zone. So I can set things in the pre-phase before it, right? And I can get to this pre-phase by using this. So at the end of last cycle, remember this is the smallest time instant. So if you have that number one step, it'll force it into this zone up here. So this is just a note on this. I've seen a couple people do stuff like this also. Do you think that makes any sense? Right? Because the one is a number. Okay? This, if your system operates correctly, should be identical to 1. Because you can't get less. That's the smallest time interval. Right? So therefore 1.2 steps should be identical to 1. Does this make sense? It does. It is currently legal. It's also bad. Right? Because what do you mean? Do you mean the start 2 cycles later? Do you just mean 2 cycles later? Right? You're not really synthesizing off this because you don't use these timing things at the synthesis. Right? All those get ignored, so it's all a simulation area. So it doesn't make sense. Using a 1-step makes perfect sense. It's saying, I want to have this signal come in just before everybody else reacts to it. Right? Everything's stable and finished for my system. I want at the very start of the next cycle, I want to go. What does it mean 2 cycles later I want to start things off? Right? You should be thinking in terms of what's going on. Maybe if there's some event down the line that needs to happen, then you should wait for that event until to do a 1-step. That would make sense. Again, time your event correctly. So it's technically legal, but it's generally pretty hated by most people on the System Verilog committee. So there's no guarantee its support will continue into later ones. So it is one of those ones that everybody kind of wants to axe. So don't build your designs off it. Somewhere in the future, it will become probably deprecated and removed. So, and again, this is really only used for simulation and testing. Your verification. All right. And we're going to try to separate these out. Initially, all the ones you've been writing as test benches fit up here. And so we'll do a simple stuff up here, but we eventually want to force things to happen either here or up here. So we do it before your logic or after your logic, so we don't get into some of these kind of, recursive loops feeding it backwards. So we're going to force it into the reactive stage. Does the timing of these things make some sense now? So when we're doing them, this is why this type of a separation happens. That's it. Your blocking is all occurring here, and these are happening here. Now the other thing that's really important is this post phase. Right? Remember I said $display happens up here in this very initial one in the active block? Right? So this is, inside this active set, that is the active phase. So they're both called active. Down here, this is where monitor goes. So if you've ever done a monitor command, and a display command, and you've noticed that sometimes your monitor shows one value and display shows a different value? Right? I don't know, has anybody used display and monitor a whole bunch? Sometimes it's nice, like you look at waveforms by looking at the picture, but sometimes it's a pain in the butt in a big picture to see it. So it's often nicer to just output, to the command line some values to say, this is what the time period is, here's the set of variables, and you tell it what to look for, right? So you do some conditional check inside your test bench, and you output the variable. And what monitor does is you can monitor a variable, and every time it changes, it dumps it. But because display happens earlier than monitor does, in the same exact time phase, they can actually report different values of the variable. So if you do an awful lot of this checking, you'll realize it's really annoying. You look at a particular time period, you've output some variable, it says 1, and then the next line on the monitor, it says a completely different thing for the same exact time slice. Right? That's telling you at the very start it was this, but it switched to this part way. Well, the way you avoid that problem is don't use display. There's a separate command called strobe. Right? Strobe happens in the same exact phase as monitor does. So you can use strobe to guarantee that it's happening at the very, very end. There is no feedback from this post. Right? So, this makes it a very nice way to do it if you use monitor and strobe instead of monitor and display. And it actually avoids all those problems. Now when you're outputting your stuff, you get a consistent picture of memory being echoed to your file or to your command line or whatever else. So just a little note, and this is again why it happens. So our basic idea is we want our test bench here, and this is where we want our logic. That separation will prevent race conditions, which will prevent weird timing data. And again, this was not possible in Verilog. You cannot in Verilog make this separation. It doesn't even have these time periods. It doesn't have a reactive set. So there's no way you could do this. We'll talk about how we get into here. We're going to make a program thing, and we're going to have time blocks that we'll set up inside, which will allow us to activate these areas and to force them in. And that lets us to separate those times out. Okay, so that's kind of my first little combination. It kind of underscores this area, and it adds this one extra kind of fundamental rule to your design. Never use #0 for time delays for sequencing. Okay, good? Okay. Now, this is actually what we're going to talk about now is both in Verilog and System Verilog, but you probably have not seen it. And this comes to the idea of generating. So let me give the simplest example that I can imagine. Let's say I have a full adder defined. So these are, each one is a full adder. And I want to make a ripple carry adder. Right? So the simplest type of system you could build off this. Right? Presume that I've got a module declared that has these, and away I want to go. How can I go about doing this? I could come into a module, and inside that module, I could just declare type full adder, full adder 1, and I could pass in the appropriate stuff, right? Imagine I had their names were X and Y, and you know, CI for C in and COUT for C out and S for my sum. You can imagine those are kind of my internal names. So I can now go .x and I could feed to it whatever its appropriate thing is. Let's, you know, for simplicity, we'll say I'm gonna hook A to it. So I've got A0 and B0. And I've got my overall C in here, and this is S0 coming out, right? And I wanna hook this one to the next unit. So I've got some wire declared here that I'll call C, and this will be, you know, a C0 carrying over, and between these two I'll have C1 and C2, and those are subscripts to tell me it's the index. Get one more laziness, and obviously copy the same things over. And then I've got, this is C out. So I could come through in here and say, okay, .x is A bit 0, right? And Y gets B bit 0. And CI gets C in, and S gets S bit 0, and .co gets C bit 0. And then I can have my next full adder, FA2, and I could set it up with its own one. Right? Now, already to me, it's tedious. But I'm just going to take this one like one step further just to go through and say, hey, look, this is A0. Where is this one going to be different structurally from the above, or is it? It's only going to be different on, is it going to be different on both carriers or just one of them?
The CN is gonna be the out.
Right? Yeah, the difference will be on my .c in, which will get C0 from the previous stage. Right? Otherwise, it'll be the same, right? Increment to C1. It'll look pretty similar. So I'm just going to put the dots, close it off. Now, F3 will follow the same exact pattern, just increment. Right? How about the last one? Right? Obviously, X, Y, whatever are going to be exactly the same. Right? Because they're feeding in. The S will be exactly the same. Right? Following this kind of central pattern here. How about my CN? Yeah, it'll still be following. So I got, you know, same kind of internal pattern. I got my .c in, which will get C bit 2. Anything else changing?
CI gets C out.
Right, so I call it what, CO, and it gets C out. There's obviously a pattern. It's a little bit different on the very last one and the very first one. But other than that, I mean, and all the ones in the middle, FA2 and 3, it's exactly the same. Well, what if this was a 32-bit adder? I'd have two different ones, but the 30 in the middle are going to be a really obvious pattern. It's pretty tedious for me to have to do that. We agree? So now I want to be able to not do this by handwriting them. I obviously could handwrite them, and that's the way most people are going to do it. I'd like to be able to tell the system to generate these. Right? So this is why Verilog gives us the command generate.
Is that different than GenVar?
So GenVar is the variable for generate.
Oh,
So GenVar, right? I can tell it that, you know, my gen var is I, or an int I, right? That tells it, this is the variable generate will use, because it needs to know how many of these things to build. There are several different ways you could do it, but they're all looping structures. So unless you have a good reason otherwise, I strongly suggest you use the for loop structure that's within here. I've declared my gen var I. So now what I want to do is I'm going to tell it where to go. Now, if you think about this, it probably would have been better if I had numbered this, say like 0, 1, and up to 3, just for niceness. So I would build this one. So this code, because it's not part of my pattern, I would stick it in. 0 is done. So I want to pick up at the very first one after that, the next bit. So I'm going to set this I to be equal to 1. All right? Now, the very last one, I'm going to copy it in. Because again, it doesn't follow the exact pattern. So I'm going to kind of just specify that one. It's the ones in the middle that are going to work. So for 4 bits, I want to do 1 and 2. So in general, if I had n bits that I wanted to handle, I would have I less than n minus 1. Do we agree? So for 4 bits, that's 4 minus 1 gives me 3. I'm less than, that means I can only run up to 2. Make myself enough room there. Do we agree? I can do that I++. I can't in Verilog. I technically would have to say I equals I plus 1. But in system Verilog, I can do I++. So one of the things, and I don't necessarily want to go through every single one of these ones because it's programmatic, but system Verilog adds a lot more C++ constructs that's in here. So for instance, you actually have classes. You can declare virtual functions, right, with all the inheritance inside it. You could not do that in Verilog. So I could make a virtual class that's for memory, and I could have a read and a write function that I don't show the implementation for. I just, for the read function, I pass an address to it. For the write function, I pass data in an address. But I don't stipulate how to do this. And then, right, I can now polymorph this, and then inside I do another virtual function where I now specify the contents of read and write. What does that mean? So that would allow me to specify. That's kind of a nice thing because it's as close as you're going to get to specifying an interface, and it's really the only part of it you care about. All right, so a virtual one, you're forcing, there are certain behaviors you know you're going to be able to use. And since you can polymorph them with virtual stuff, you can make a version of whatever you care about. So all these things, if you did any decent amount of C++ programming, you get the vast majority of them. There are some things you don't get, but we've already showed you get structs now, and you get type defs, and you get enums, and all kinds of fun stuff like that. But I also get little simple things like ++. Which, to me personally, that's actually, it's really tedious when you have to remember, oh yeah, I gotta write I equals I plus 1 all the time. That was one of the things that actually annoyed the hell out of me. So, okay. So I've got my generate, I've got my for, and I've got it so that I know I'm generating the correct number of these. Now what I'm gonna do is I'm gonna tell it to generate for me FA. Right? That's my data type. So I'm going to, in this case, if n was equal to 4, I'd be generating 2, because I go from 1 up to 2. So it'll generate 2 FAs inside here. I want the name to be FA1, so I can tell it FAI, because I is my index for this generation.
What did you say again?
What's that?
What did you say?
Well, n is something I would have to, a parameter I pass, how big is your ripple counter, right? So assume I'm making a module here, ripple adder. So somewhere up here I've got module. I can spell module. You know, whatever, you know, maybe I call it ripple or rip, right? And I've got my parameters. Right, so I've got n and whatever its default is. And then I've got what you're gonna have for the rest of your pass to it. Right, so n is just my parameter that carries through. And I was just making that generic because then we could say, oh, if it's 4, it's this. But you can now see the power of where generate comes in. Because now if you want 32 of these things, you know, what it would take to do it, I'd have to, for 32, I'd have to write a completely different one where I copy and change those things manually. However, with generate, I can actually have one module. And you call it with a parameter size of 4, and you get a 4-bit ripple carry adder. You call it with a parameter 32, you get a 32-bit ripple carry adder. And I don't have to write anything new. And so that's actually a really very nice feature for us when we're going through and building stuff. Okay, so I can get a unique name off of it. Technically speaking, according to the Verilog standard, I should be able to leave this off and be totally okay. It should automatically generate names for me. Now, my personal experience with Vivado has been every time I have tried to do it, it crashes. For some reason, in other places where it's supposed to pick the name, it actually does. But in this case, I've noticed it never does. Okay? I have noticed if I give it a base name, at least when I've done it on 2014's version, which is the version I have available up in my office, it actually appended the number on it automatically without me having to tell it to. When it was running through, it goes, okay. But then you have to be real careful not picking the same thing here. You know, so I call it like my FA or something like that. And it appended the number automatically onto it instead of having to explicitly tell it.
It didn't start with 0.
No, it actually picked the correct one. So, I mean, why it can handle one case but not the other, both are part of the standard, I mean, somebody did whatever. At some point along the line, they'll figure it out and fix it. But I've just noticed for myself, it doesn't. Now, this is, if I can, well, maybe we'll finish this out, and on the names, I'm just gonna put a note to here to talk about begin. Because that's kind of a, there's a special thing that happens with begin if I've got loops that I'm building, but I don't want to distract from this to do it. Now we need to parameterize this. And I'm parameterizing in terms of I. So if I look at this, right, so I've got for FA1, I've got all of them are going to be the same as 1 is, except for its input, which is coming from the previous stage. So in this case, I would have dot x, and dot x is going to be coming in from A, I. Right? Identical to my number. So for this one, when I is equal to 1, it'll take from A1, which is exactly what I wanted. Y will take from BI. Right? My CI will take from CI minus 1 from the previous step bit. Some will get, or S inside. And outside, I call it S. And then C out, I will take my C, and this one uses bit I. We agree? And it'll do this for two values of I, because that's what's allowed. And then I tell it N generate. Right, so now it knows that's the part I'm doing. It knows what it's, the variable it's using to enumerate these. It knows the range to calculate them on. It knows what to build. It's got a built-in naming scheme that makes them unique, and away I go. It now builds as many of these as you want. That's a nice feature. Now, it depends upon you being able to easily enumerate these, and notice you have the wires between them as well. So, for some of these, right, I'm going to have this handled up here, right? I'll have, input, logic, and for my A, how big is it going to be? We agree? So some of these are going to be pretty easy, how I change them. I can do this. This is input logic. This is input logic. This is output logic. And then I'm also going to have on the two unique cases, Cin is input logic 1 bit, and Cout is output logic 1 bit. The only one that hasn't now been handled is C. All right? So how do I declare C?
Just an output,
Function of N.
or is it an out?
So it is a function of n. Right? For my ports, I've got three choices, right? Input, output, in, out. Which of the three do you think it is? How many people think it's an input? How many people think it's an output? How many think it's an in, out? Some people didn't raise their hand.
Which one is
Is it CI or CU?
Just C.
Oh, just C.
In this case, the people who didn't answer are right.
Oh.
It's not an input, or an output, or an in-out. Why? It's not a port. Nobody can see it from the outside.
Oh, it's just an internal one.
It's an internal wire. Right? You only declare ports if somebody from the outside can either give it to you or get it from you. Other than that, this box should be opaque. That's an internal wire. So how do I declare it?
It's just a logic outside.
Okay, it's a logic. Now what do I do?
Times 1. Last one.
See if everybody, do we agree with this? Do we disagree?
Wait.
It's close. This will work, but it's wasteful.
Oh, is it only because we're using two, so therefore we need,
Yeah.
So how many of them are we using?
oh, I guess,
This one uses 0 on the input and 1 on its output.
yeah,
And this one uses, the next one, which I didn't show here, right, FA2 uses 2, right, 1 as an input and 2 as its output.
so I guess we only need three, 3 minus two.
Yeah. because the output of the next stage goes to C out, so you don't need that fourth. You're only counting the ones between, right? So since it's between, if there's n objects, there's n minus 1 wires in between, right? And so since we number from 0 to 1 less than however many there are, I'm go from 0 to n minus 1 minus 1, which is n minus 2. Does that make sense? Okay. So now at this point, everything's declared. Boom, universal ripple carry adder. Right? And you can make it as big or small you want just by changing that parameter. That's a nice feature. So generate is a really great command. Generate is somewhat dangerous with more complicated structures. It is sometimes even more helpful with a big complicated structure, but making it work right is a lot harder. And we do some more complicated ones if you do advanced digital logic. So in advanced digital logic, I make you make a conditional sum using generate. Right? And conditional sum is a more complicated one, but it's faster. Right?
So in what cases would it be more beneficial to use generate instead of having, like, when you call FA and then do, like, 3, 0, and then, like,
Yeah, well, if I don't do generate, I have to build them all manually.
yeah. Well, there's a way to do, kind of call them all manually, but at once, I guess. If you do like FA and then 3, 0, and then name it, I guess.
So you have to declare it in such a way that you can pass multiple wires to it. Right, that's on them. So I would have to declare some larger structure. How does it know to interpret that? So if I build a full adder, how does it know how to connect between them? So if I just call it with the numbers without having any structure on how to generate them, it's not going to know how to do it. Right? And the big problem on that one is if you were to just pass it to it, it's not going to know the interconnecting wires of where it's going. I could write something that would recognize that and say, oh, hook these up. And it could hook up everything, but it wouldn't know what to do with those. Right? Because if you wrote something to recognize FA with that, it'll recognize the A's, the B's, and these. Right? But if I told it to do CN for its CI, then it would do it every time.
Yeah.
Right? So it wouldn't know how to handle that situation. So that's why, if you want to do it, we created the generate to be able to let you build those according to a pattern. All right, so if this sounds good, imagine I could also have written, instead of writing a module for this, I could have written code that just explains what a full adder does. So I could make, for instance, an always block for these. Can I use generate to build an always block? Make multiple of them? Sure. Yeah, why not? Right. So I could, instead of this, I could have had inside, these would have been always cones to describe those special cases, and I would have inside here an always combinational logic. Okay. And then I would have to just inside here logically, right? So I'd have begin, lowercase b, and I'd have to stipulate what's going on inside it. So what's the function to generate S? So in my case, it would be an S I, the ith bit of S, and that's going to be equal to, I have A's ith bit, B's ith bit, and C's ith bit. And how do I connect them all together? You either punish or you carrot to reward. Carrot is XOR. So why is XOR the correct one?
Because if you're saying you overflow to zero, you get that one.
XOR tells you odd or even. That's what XOR does. XOR is a 1 if the number of input bits is odd, and the XORs is 0 if the number of inputs, if the number of ones on them are even. So in your simple sets, right, you have 0, 0, 0, 1, 1, 0, 1, 1. When it's odd, you get a 1. But if you go to higher order bits, right? Odd, odd, and even, even. No matter how big you go, you just count the number of ones. If it's odd, then it's set. Does that make sense? It may seem surprising and strange to you, but all of you have used this before. Use it for parity bits. What's the two types of parity? Even and odd. So why does pumping all the wires into XOR work? Because XOR tells you even or odd. It tells you odd if you just use XOR. If you use XNOR, just flips it, but it tells you it was even. That's why the two types of parity are out there. It's XOR or it's complement. That's why it works. So XOR is really truthfully even or odd, if you think about that basic functionality. So all I'm doing with my bit, the sum bit is saying how many ones were passed to me. This is a full adder. I got 3 bits passed to me. If 2 of them were ones, that 1 will show up in a carry, but it's even, so it's not going to show up in the sum bit. It was 0. So you're only going to see something on the sum bit if 1 or 3 of them was set. That's why XOR is the right choice. How about for my carry? Right? So my carry out goes to C, and this one, let's see, I was using C, actually I want CI minus 1, right? From the previous stage. It was actually coming from the previous stage's carry. And I'm generating CI, I read CI minus 1. So what should CI be? Right? So what do I want for this one?
Any two.
Any 2,
Yes.
right? So how do I make sure 2 of them are correct?
You could do, something and.
So I could do and 2 at a time, right? There's only 3 of them, so I could do and 2 at a time and kind of combine them together, right, by using or. Right? That'd be one way to generate. There's a couple different ways you could generate them. But it would be easy enough to say, AI and right, BI or right. Just give me my conditions 2 at a time. You can also use what's called propagate or generate. Right? So this is used for some of the pre-calculations. But if you look at them, right, for these 2 bits, you can just take these 2 initial bits and find out whether it's even or odd. Right? And if they're both, right, so if they're both set, then that one is going to generate something. Right, it means it'll generate a carry to the next stage. If one of them is set, then it's going to propagate. So you can also write this, so if you pre-calculate G, their A and B are both set, then I can just say this is generate, it'll make one of these carries, or propagate, and that one has to be not only propagate, but now I have to do it and the previous stage of Ci minus 1. So, and generate is just defined, just as a side note, generate is equal to the A and B, and propagate is A or B, with the appropriate subscript. That make sense? So, obviously this is I. You could put it in square brackets, more correct, but the reason why I mentioned generate and propagate, have any of you seen block carry adders? You've seen ripple adders, right? And what's the problem with a ripple adder?
So,
Slow, right? 32 bits, you have, 31 wires in between it before things ripple down, right? But we know in advance that all logic can be done in 2 levels, right? Do we agree? We know that as a result because that's actually what our standard forms tell us. Now, the reason why we don't, that means I can technically do an adder in 2 levels of logic. There is actually a wire combination circuit that no matter how many input bits you have, will solve addition in 2 gates. There is a circuit that will do multiplication for as many inputs as you want in 2 gates. Stupidly fast, right? Constant time. Why don't we do it?
It's a whole lot of wires.
It's a whole lot of wires, and those gates get arbitrarily big. So what you get is, I've got a whole ton of wires coming in, and I got a whole ton of wires coming out of these gates. They're gigantic, which gives you a problem called the fan-in and fan-out problem. The fan-in problem is there's too many wires coming in. Well, what happens if every one of those wires has voltage on it? Right? Think of it like, if you think of wires like hoses, right? And having voltage on it means that water's flowing down that hose. That means my gate, I could have 32, 64 wires coming into my gate. That means I've got 64 hoses worth of water flowing into my gate. I got to get rid of that water somehow. We call that sinking the current. Okay? So now my one gate has a ton of current flowing through it. What happens if I have too much current flowing through a gate? You let the magic smoke out, right? If you've ever put too much current through one of these circuits, you know the uniquely horrible smell of burnt IC, right? So this jokingly is called the magic smoke. So the second you smell the magic smoke, and that burnt semiconductor is an unmistakable smell. And after you smell it, it no longer works. So clearly that was the magic smoke that you let out of the chip that caused the chip to run before, and it doesn't run now because it's out. That's kind of the running joke. So if you ever hear people talking about the magic smoke, that's what they're talking about. You burnt an IC, and it's no longer working. Well, the fan-in problem is it's really easy to burn an IC. You got too many wires coming in. You just can't sink that much current. And even if you could sink that much current, all of that current's now flowing into your ground. So that goes into a ground plane. What happens when you have a lot of current flowing through a ground plane? Well, a ground plane is like a wire. Let's assume it was big enough to hold this current. It won't be, but imagine for a second it was. I've got a huge current flowing over this resistance. What happens? Current running through a resistance causes a voltage drop. So you get a whole ton of current flowing through a resistance. You now get a big voltage drop. So your ground starts to float. Okay? Which means your gate's ground is floating, which means it's no longer properly measuring where a 0 or a 1 is. So even if you somehow were able to make an indestructible gate, the gate's ground would float And you still wouldn't be able to calculate the right answer because you put enough current through that thing, it's going to float it up to a 1 anyway, logically, which means it's not going to be able to read a 1 versus a 0. So not only will it blow it out, even if it couldn't blow it out, it still won't read a good value. So basically, fan in is a huge problem. Fan out is the flip. Imagine I have to send my wire to 64 different gates. Right? Now I have to supply the waters to 64 hoses. Right? That means I've got to have a huge amount of current I'm switching. Well, first off, that means I'm sending so much current through, I'm probably going to let the magic smoke out and blow myself up. But the other one is, as I start letting that much current go out, what happens to the source that I'm drawing from to pipe this? It drops, right? As you increase the current going out, your voltage drops, which means your 1 is no longer a 1. You can only supply so much before you change your output currents. Right? So therefore, the reason why I don't build these things is because I run into one of those two problems. Well, then I go, okay, what if I back off slightly? Instead of trying to get 2-level logic, can I try to at least speed up my ripple adder by generating in advance some of the carries? Or at least carries in groups so I can make them faster. This is where generate and propagate comes. Now, A and B are available at the instant things come in. Carry is the thing that takes a while to generate. So for every one of these bits, these are very simple to build. There's nothing big or complicated about them. So that which I can calculate in advance, I calculate in advance. Right? I do that very fast. It's available instantly. So the second your carry, the input carry, comes to me, I can instantly react to it with a very simple gate. Right? That make sense? So the reason generate and propagate become useful is it makes them as fast as you can make them. And then I can kind of pre-do these. I can make a circuit that'll calculate these in blocks of 4 at a time. And so if I limit it to a 4-input prediction, then, I can do all these different blocks of 4, and it'll take significantly lower time. It takes, if it was 32 bits, it'll take 32 divided by 4, or 8 time units to get done. That's still linear growth, but it's with a smaller constant. So it's significantly faster, and my gates are still small. So it improves performance without doing it, and generate and propagate are the key to those speed up factors. So it's worth at least noticing where you can use them. Good? That's a little bit of a digression, but if you never saw them, it's an important digression to understand. Because fast ripple adders use this. And they're called carry look-ahead adders, or technically they're called block carry look-ahead adder. So if you see that, CLA or BCLA for it, that's carry look ahead. It means I'm trying to guess what the carry is going to be before it hits. It lets me calculate them quickly, and it uses this calculation. All right. So anyway, I could stick this one in, and now I'm good. Now, here's the trick though. When I generate these, when I did the previous one, I had the full adders. I could name them. How do I name these? I'm going to get a whole bunch of these combinational blocks, but they have no names. So when you generate them and you look at the objects being created, right, I'm going to see a whole bunch of these combinational blocks that are out there, but I won't know what they are. How do I know which one to connect to which one, so when I'm doing a layout, I get a good layout?
The name after the PQ.
But colon, and you can list a name. And that name, I can still use the same I inside it to specialize the name to it by its index. So, that colon name after the begin becomes an important thing. That's why I wanted to mention over here. Why I said remind me to get to that point. That's how I name any of these. So if you have any type of a structure inside here that's gonna use code, right? I gotta make sure it's got a block that it's gonna happen within, but then I can still name them by using this context. And otherwise, it's really hard to track what the synthesized logic is afterwards. We good? All right, so I have two more things I want to mention today. So if we're good with this, I'm about to erase this. Okay, nobody saying anything? I'll take this side. I want to start talking a little bit about test benches for this type of combinational logic. So one of the first things I might have to do is to generate a clock signal. Right? So imagine I come in here and inside I make, logic, clock, right? And then let's say I do initial, clock equals 0, forever, wait, let's say I do this. Okay? First off, legal, illegal. Assuming somewhere up here I, define cycle, whatever, 10 or whatever I make it, right? So that just allows this to be whatever my cycle time. Cycle time divided by 2, half the period, so it's a 50% duty cycle for my wave, for my clock, right? Is this good? It's legal code, right? Forever just means keep doing this thing, right? There is the forever loop. So this is just a forever loop, and it just waits half a cycle time and flip it. Totally legal. What happens at time 0?
You don't have any initial.
At initial, I got this, right? All of you look like I've created something deliberately devious to give you a weird thing, right? Now you're all smirking, which means yes, I am trying to mess with you, right? So the question is, how am I messing with you? What's the potential thing that could be weird that happens here? I mean, doesn't initial force that to be 0 right at the start?
I guess there's like a very, very beginning.
There's before the initial.
Yeah.
Okay? Remember we talked about those time periods?
Yeah.
This initial right here, this is an assignment. Remember our little time chunks, right? We've got our pre-section. I can type pre, right? We've got our active set that's in. This is a non-blocking assignment, right? So that means it happens in the active set in that very first little of the 3 chunks. That's where this occurs. What happened before that? It was X. This specifies, right here, that clock is initially X.
Can you just initialize there?
I could. So I could say right here, clock equals 0. Believe it or not, this has different performance than that does. The difference is this one has 0 right at the start. With the following caveat. That's the official Verilog standard. When the system Verilog first came out, and for the first about 5 years or so it depends how old your system is, right? They didn't properly implement it. So logic still did the same as this did. They didn't do this assignment here until there. So it was still X initially. The only one who actually did it right is Mentor Graphics. Which, if you ever wonder why I keep saying I like Mentor Graphics, the reason is they were right from the start. They implemented the standard, and they were the only one who implemented the standard correctly from the start. I just hate dealing with something I don't know if it's going to behave the way it's supposed to behave. So you just have to note, by this point, I think everybody has fixed theirs so that they're now different. This one happening in the pre-stage, this one happening here. The difference between those two is if this is set in the pre-phase, that means it looks like for all time it's been a 0. If it was initially an X and then it goes to a 0, technically this will generate a negative edge. So this generates a negative edge of the clock at time 0. So if you've ever done a simulation, this actually happens to people when they're doing like CompOrg and they're making their system. And I usually tell people, put in a init or a running flag in there so that you don't count the first couple seconds of behavior and you just kind of clear the whole thing out. It's actually to avoid this problem because most people set their clock up wrong. And there are times you actually want this behavior to happen. Right? Sometimes you want a negative edge right at the very start. This will give it to you. Right? So logic is 1 bit, right? It's going to be a 1-bit variable. There's also another one called bit. So if I switched from logic to bit, do you think it would behave exactly the same? I mean, they're supposed to be the same, right?
It's only 0 or 1, right?
Bit only allows 0 or 1, so there's no X. So what does it define at the start since it can't pick X? It's 0 by default at the start. So if I put bit in here, I don't have to do any assignment. It's automatically a 0 because that's the only choice it can make. No starting neg edge again. I don't even have to do this. I can actually do that, which means I actually can remove the big in end. So it's just a one-liner now. And it works perfectly fine. Because it has no choice, because bit can only be 0 or 1. Logic can technically be all 4.
Is bit different than bool?
So functionally, they're essentially going to work the same, right? But I would use bit. And the reason is there really are, when you're building these, bit forces you, you're saying, I want you to synthesize something like logic, except I want you to restrict it to 0 or 1. So you force the case. Logic will handle almost every other case. And the only other one you actually need, you still need wire or try. Right? Try is just a polymorphed wire. The only case you need these is for the case where you have multiple drivers. Right? I'm building a bus. So you need these for buses. You cannot use bus logic for a bus. So you can't have an in-out that's logic. You can have in-out that's a wire. You can have in-out that's a try. Right? So if you are actually doing a bus where it's an input-output state and multiple people could be writing to the same device, multiple drivers to it, then you have to use wire or try. So this kind of underscores that kind of thing. Logic is for like 99.9% of everything you do. Bit is really if you just want to restrict it to 0, 1. And wire or tri-state is if multiple different modules could be driving it in some bus fashion. So you want to allow multiple drivers. Neither of these can support that. Therein is how you are going to pick your elements. Make sense?
Between wire and try.
technically speaking, there's not much of a difference at all. Wire itself is the base class. Tri is specifically done if you're building a tri-state gate. So when you declare tri, you do it as a step towards building a tri-state gate on it, whereas you can also just build a tri-state gate and have it drive a wire. But you can actually synthesize a tri-state gate using tri. So it's really just, specialized. I could have a wire that could have multiple drivers. I could have a tri-state gate that is driving, one of the ones driving that wire. That's really the difference where it comes in. Is this the part of this whole device that's synthesizing the tri-state gate? But other than that, that's why I kind of lumped them together, because, you could really build that tri-state gate in either way. That's kind of more of a how do you want to do it. Most people in the past would use wire. It's moving more and more towards using tri. Right, because now you're being very explicit. The reason why you're doing it is because you're going to have a tri-state gate driver, as opposed to you just forgot and forced to have some type of a logic system going on. Okay, we've got a few minutes left. I'm going to stop at this point. Right, if you've got a circuit to show me, so I know that you're done, then this is a good time to show me. Sound good?